Welcome to the lecture series on deep learning in artificial neural networks. In this video, we look at the loss landscape, and the question we ask is, why are there so many saddles? Just as a reminder, a saddle point is a point where the curvature in one direction is negative and positive in some other direction. So why should we be interested in saddles? Well, if you do gradient descent, then the descent gets very slow in the neighborhood of the saddle before it takes up speed again. The reason is that close to a saddle point, there's a region where the gradient is very, very small. It's exactly zero at the saddle, and it's small nearby. So gradient descent can get stuck at a saddle point. And this is the reason why we are interested in saddles. So the question we ask is, how many of such saddle points are around? And the claim is there are many more saddle points than minima. And there are two arguments to support this claim. The first one is a statistical argument based on the Hessian matrix, and the second one is a geometric argument based on the permutations that we have seen in the previous video. So let's now discuss the first argument, the statistical argument. So at the minimum, or more generally at a critical point, the gradient vanishes. And now we look at the second order derivative at this location. If this second order derivative is positive, then we have a minimum. If this second order derivative is negative, we have a maximum. And this statement is valid in one dimension. However, we have more than one dimensions. We are in high dimension. Since the Hessian matrix of second derivatives is symmetric, it can be diagonalized. And then we are in very high dimensions. If we are in n dimensions, we'll have n eigenvalues, and it's the distribution of these eigenvalues that characterizes the properties of the critical point of a potential saddle point. The standard situation of a minimum is that I have these n eigenvalues, and all of these eigenvalues are positive. They are all positive. Then we have a minimum. Now, a first order saddle point is such that most of the eigenvalues are positive. It's positive in n-1 dimensions, and this means that the surface has sort of the characteristics of a minimum in n-1 dimensions, and then it goes down in one dimension. And this is a first order saddle point. The second order saddle point is that the surface goes up in n-2 dimensions and goes down in 2 dimensions. Now, this is a very strange sketch because we humans can only visualize things in 3 dimensions. So each arrow here really means, or each doublet of arrows really means it's a dimension where it goes down, and then there's another dimension where it also goes down. And then there are n-2 dimensions where the arrow surface goes up. So this is a second order saddle, and more generally we have a kth order saddle where the surface goes up in n-k dimensions and goes down in k dimensions. So far I've just talked about minima and first order saddles and kth order saddles. Now the core of the argument is a statistical one. Suppose that you create eigenvalues randomly with mean 0. Then, because of the statistics, it's very unlikely that all eigenvalues have the same sign. Therefore, it's unlikely that all the eigenvalues are positive, and therefore it's unlikely that they have a minimum. It's fairly rare that only one eigenvalue has a different sign than the others. Most eigenvalue combinations will be such that some eigenvalues are positive and some are negative, which means we have a higher order saddle where in some dimensions the surface goes up and in other dimensions the surface goes down. So there are specific mathematical models and models from physics coming from spin glasses, coming from random matrix theory, coming from Gaussian processes that all arrive at the following type of picture. Now this picture is not a one-dimensional picture. This is some abstract direction of weights. It's not one specific weight. It's just to show a couple of points. And the first point is there are several good minima that have all very low energy. And then there are a few first-order saddle points that go down in one direction and go up in many other dimensions. And then there are second-order saddles and higher-order saddles that all have a bit higher energies than the minima. And at the very end, there are also one or two maxima that lead to the highest critical points, the points with the highest loss, the point with the highest energy in the physics sense or error in the sense of artificial neural networks. So the summary of the statistical argument is that for these random matrix theory or spin glass systems, we think of the n eigenvalues as n random numbers. Since it's rare that they all have the same sign, it's rare to have maxima or minima. Most points of vanishing gradients are saddle points, and most high-order saddle points have multiple dimensions of escape. Well, most high-error saddle points have multiple dimensions of escape. The lowest saddle points are those that are first degree saddle points, and these have only a single dimension of escape. High error saddle points have multiple dimensions of escape because they are higher order saddles. So this is the result of this kind of random matrix arguments, or generally random systems argument. But then the question is, what is the random system here? Well, you have to think about it a little bit. But basically the idea is that the data is random because you don't look at the data when you generate your system. So the data is independent of the design of the system, and then during learning, remember, it's the weights that are the free parameters. It's the weights that can adapt. So the data is a constraint, is a combination of random constraints onto the optimization problem. Remember that there are two different arguments. So far, we have looked at the statistical argument. We have analyzed the eigenvalues of the Hessian matrix. Now I would like to focus on the geometric argument. The geometric argument is linked to the multiple minima that are generated by permutations. So if you have one global minimum, then you can generate many other global minima just by permutations of the hidden neurons. And the idea is that between these permutation minima, there are saddle points. Let's discuss this a bit in more detail. So for the geometric argument, I will focus in the following on global minima. So we focus on global minima, and then we look at saddle points that connect two different global minima that are equivalent because they arise just from permutations. This is just a reminder how a saddle looks in 2 dimensions, and in the level picture, in the niveau line picture, you see that we have 2 minima separated by 1 saddle. And now the question is, if these 2 minima, if you think of these 2 minima as global minima that arise from a perturbation, how can we construct the saddles between those 2 minima? So let's look at a specific network, a small network with 4 hidden neurons in the first layer. Each neuron will implement a hyperplane, and here is the configuration of the 4 weight vectors of these 4 neurons. I have here neuron number 4, which is the brown neuron, which implements this brown weight vector, to which corresponds the brown separating hyperplane. And then I have the blue neuron, which is neuron number 3, which implements the blue weight vector and which corresponds to the blue separating hyperplane. Now, suppose that this specific configuration, this configuration here, with the 4 weight vectors, the blue one, the brown one, and the 2 black ones, corresponds to 1 global minimum. Then we know that there is another global minimum, and this other global minimum corresponds to a permutation. So it's the same configuration of 4 weight vectors, but now the brown one points downward and the blue one points to the right. To keep things simple, let us consider a teacher-student configuration. So here I have a teacher network characterized by 4 hidden neurons that implement 4 weight vectors. For example, the blue neuron could implement this weight vector here, and then the other neurons, the other 3 weight vectors. And all the output weights have been set to 1. This configuration is called a committee machine because it just takes the average over the outputs of the hidden neurons. And then we have a student network which has exactly the same architecture, exactly the same number of hidden neurons, the exact same inputs, but it has 3 weights in the second layer, 3 weights in the first layer that need to be learned. Now suppose that after learning, the student network is perfectly aligned with the teacher network, so that the student network has 1 weight vector that's perfectly parallel to this one. It has another one that's perfectly parallel to this one, parallel and of the same size, and same for the other 2 hidden neurons. So sometimes instead of drawing the full weight vectors, we'll just draw lines. The blue lines will refer to the directions of the teacher network, and the red dashed lines to the directions of the student network, the weight vectors of the student network. The stars correspond to the positions of the hyperplanes that have been implemented by the teacher network. So this is the situation now. We have a teacher network which implements the 4 blue hyperplanes indicated here, represented by these 4 black weight vectors, like this one here. Then we have the student network, and we assume that the student network has already perfectly learned, so it has 1 weight vector, the one of neuron number 4, that's perfectly aligned with one of the student weights, and we have another weight vector, number 3, that's also perfectly aligned with that of the teacher, and the other 2 weight vectors are also perfectly aligned with those of the teacher. And now we force the 2 weight vectors, W4 and W3, to move closer to each other. In other words, we decrease the distance while we let the other student weight vectors freely move so that we are always at a minimum loss configuration. And so this decrease of the distance will be performed very slowly. And this is what you're going to see on the next video. And at the end, we'll be at a configuration where this weight vector has moved and this weight vector has also moved. And when the two are really identical, this is the point that we will call the permutation point. And so here is the video. You see in blue the lines of the directions of the weight vectors of the teacher. You see in red the two weight vectors that move to each other, and then they are together at this permutation point, which is reached again now. So a permutation point is the moment when the two weight vectors that have been moved together are identical. And in this position, I have two weight vectors that are identical. That means I can exchange the indices of neuron 3 and neuron 4 at no extra cost because they are the same. Let's now do this step by step again. So the idea is that we slowly decrease the distance between two of the weight vectors. The other student vectors, the red lines, can freely adjust so that we always stay close to a minimum loss configuration. And while we do this, the loss increases. Now, at this permutation point, we interchange the indices of these two weight vectors, and then we can basically relax back, but with exchanged indices. Now let's look at this in terms of the error surface. So at the beginning, the weight vector W4 of this student looks in this direction. So let's draw here the two components, W42 and W4 and 41. W41 here, W42 here. So this is this weight vector. And now this is the configuration of the teacher, so we are sure that this is a minimum. And then while we move up, we actually increase the loss until we arrive at this situation where the loss is now maximal. And at this point, we interchange the indices, and now we push this weight vector, the weight vector of neuron number 4, towards the position that was previously held by the other weight vector, the weight vector number 3. So you see you have the classic configuration of two minima, one minimum here, one minimum there, and the path that we construct is a path towards the saddle point. So on the way up, we approach weight vector 4 to this permutation point, and then at this permutation point, we interchange the indices, and we shift the weight vector to its final position over here, which is this position, and during that shift, the loss goes down again. So far, I explained what we mean by permutation point. And now the real counting argument starts. The permutation points are saddle points. The claim is there are more saddle points than global minima. And then now let's count these first order saddle points. Now, once the weight vector number 4 and the weight vector number 3 are the same, it's a little bit like having only 3 neurons left instead of 4. So in the end, we have no longer 4 positions that we had before, but we now only have 3 positions. But these 3 positions must be enough for the 4 indices of the 4 weight vectors. And that means one of the positions must be used twice. And this can be transformed into a counting argument. So let's now start and count these permutation points. We consider a layer with n hidden neurons. So the indices are, say, 1 to 5. I have 5 neurons in that layer. Now assume we only have 4 positions. So first we have to decide which one of the 4 positions we are going to use twice. So we have to double one of these positions. Well, we have n-1 possibilities. We have n-1 choices. And now we have n weight vectors. We have n indices, 1 to 5, to distribute onto these 5 positions. And these are n factorial possibilities, but the order in which we occupy this double position doesn't matter, so we have to divide by 2. And so this count now is a lower bound for first order saddles generated on the connection between permutation minima. So far for first order saddles, and this is the formula we found. Now let's do the same for second order saddles. Again, let's assume we have 5 indices to distribute, but now assume we only have 3 positions. So there are 2 possibilities. The first one is to say, well, we have 1 position that's actually used 3 times. In this case, we have a certain number of choices of doing this, and this is this choice here. And then we have to distribute these 5 indices, and this gives this factor where the denominator comes from the order that doesn't matter for the placement of the 3 indices here. Now the other possibility is to say we actually have 4 positions, and 2 of these positions are used twice. Well, that means we have that many choices, and now we have to distribute the n factor. We have to distribute the 5 indices. That means n factorial possibilities, and we have to account that the order doesn't matter for those that are used twice. So note that in both cases we have a factor n factorial in front. Now why is the n factorial important? Because the claim is there are many more saddle points than global minima that are generated by permutations. There are n factorial of these minima that can be generated by permutations between n indices of neurons in one hidden layer. And now the theorem says, well, for a kth order saddle, this is the additional factor beyond the normal, already very high number of global permutation minima. And this is valid for k smaller n over 2. So this is valid for k equal 1, first order saddles, for k equal 2, second order saddles, and so forth. And so here's the summary now. Suppose we have a network with m hidden layers and n neurons per hidden layer. And suppose we have already found one global minimum, then we know that there, because of permutations, there are at least n factorial to the power of m minima with the same loss. That's a lot. But there are even more kth order saddle points. We have this factor that's the same as the number of minima, and then we have this extra factor in front. Thus, there are indeed more saddle points than permutation minima in a network of n neurons per hidden layer and m hidden layers. So now we arrive at the following picture. In a deep neural network with m hidden layers, n neurons per hidden layer, we have an absolutely huge number of equivalent good minima. Say, these are the real global optima, and there are many of these. And then the statement is, well, there are even more of these first order saddle points. And there are even more of these second order saddle points. And there are even more of the higher order saddle points. So the landscape is really full of these critical points, and saddle points are much, much more frequent than minima. But minima are also frequent because of these weight space symmetries, because of all the possible permutations. So let's finish with a little quiz. We have a deep network with many neurons. The claim is such a deep network has a huge number of equivalent minima and even many more saddle points. And of course, this is correct. Second statement, in a deep network, gradient descent is slow, close to a saddle point. Yes, this is always correct. And close to a saddle point, there's only one dimension to go down. Well, this is not correct. Most of the saddle points are higher order saddle points. Then there are many dimensions, many directions in which gradient descent can escape, and it will escape towards lower saddle points or lower minima.